Hello. So, we're talking about projectile motion, and this is subsequent to talking about two-dimensional vectors. And projectile motion is probably the simplest version of two-dimensional motion. And the reason why it's the simplest version is that, yes, it's moving in 2D, but we can treat each of the directions of its motion independently, and it only experiences a constant acceleration in the vertical direction. Okay? So we have a sample projectile here. This could be a lot of things, all right? But the key is that whatever this thing is launching with some initial velocity from one point and then going along the dotted red line and then maybe returning to that point or any point in between, depending on whether it's, being thrown up onto the top of a building or whether it's being thrown off of a cliff or any of those things. In all of those circumstances, okay, it's only being affected once it's launched, okay, by the acceleration due to the gravity of the Earth. So, definition of projectile motion, there it is in text. So it moves along a curved path, specifically a parabolic path, near the surface of the Earth and only under the influence of gravity. This might sound at least a little familiar, and that's because when we were describing objects in free fall, so we dropped a ball or we threw a ball straight up into the air or something like that in 1D motion, we said, oh, well, the condition for free fall is when an object is only under the influence of gravity. And that's true on the Earth. I suppose it's true on other planets as well. And you would get a similar kind of behavior if you, instead of throwing it straight up, you chucked it off at, some angle to that vertical, for instance. Okay? So projectile motion is just a slight tweak to something that we've already become familiar with. So what are some examples of projectile motion? Well, I can tell you a few examples that are projectiles, right? If we have a little guy here and he's shooting a basketball and it goes into a hoop here, okay? Here's the backboard. Well, then that's a projectile from the moment it leaves his hands to the moment it starts colliding with something else, right? And why am I so specific about that? Well, the reason I'm so specific is that while it's in his hands, clearly he's pushing on the ball to get it up to its launch velocity. And so there's an acceleration other than gravity acting upon that ball. And likewise, once it hits the rim or the net or whatever, as it's going in on this end, hopefully going in, that again is an acceleration that is not due just to gravity. So from the moment it leaves the hands to the moment it hits some portion of the basket here, it is a projectile. But on either end, in that instant, then it's not a projectile anymore. And of course, different accelerations come into play. We'll talk a little bit about those, sort of the causes for why this thing becomes a projectile, not too long from now, after exam number 1 in the course. But for now, just focus on the motion between those 2 points. Okay, other things. Well, what's a projectile? Well, we could throw a rock into the air. We could throw a basketball into the air. We could kick a soccer ball off the top of a building. We could throw a television into a dumpster. We could do all sorts of things. The one thing you want to be a little cautious of, though, is situations where even when an object is in the air, it is not just under the influence of gravity. Take, for example, a rocket. I will do a really, really great picture here of a space age comic book rocket with a bunch of stuff coming out the end, okay? And if you think about that, well, it might, go wandering off, okay, and do some sort of parabolic-ish trajectory as it goes towards orbit. But it has its own propulsion, right? If it was just under the influence of gravity, once it left the ground, it would just fall right back down. And that's not a very useful rocket if you're trying to achieve orbit or anything else, okay? So if something is being propelled, whether it's a full-size rocket, whether it's a toy rocket, whether it's a person with a jetpack, whether it's a plane, all those kind of things, well, then obviously those things aren't just under the influence of gravity in terms of their accelerations, right? And so projectiles specifically only is a very important word in that definition of projectile motion. All right, so be just a bit careful there. And if you are, then projectile motion typically goes pretty well. Now, because, and I'll link to a demonstration on this. There's a couple of good ones out there. But because the horizontal and vertical components of the projectile's motion are independent of one another. In other words, you can treat the vertical motion with a set of equations of motion that are just for one dimension, the vertical one. And the form of these, other than these little, additional subscripts to specify that we're talking about the vertical direction here, okay? Other than those, these equations should look very familiar to you from our discussion of 1D motion with constant acceleration. And the constant acceleration here, this a sub y, is always just going to be gravity, whatever that is in our coordinate system. Now, in this coordinate system, gravity would be, so in this coordinate system here, gravity would be, so a sub y would be negative g, g being 9.8 meters per second squared. Negative indicating that it's downward, so in this coordinate system, on the negative y-axis. You can flip that, right? You could decide that down is positive and up is negative. There's nothing preventing you from doing that, just like there was nothing preventing you from doing that in 1D motion. Coordinate systems are a human invention for problem solving, nothing to do with nature. And the motion of the object will come out the same, whichever coordinate system you pick, okay? But for the vertical direction, well, we've got a constant acceleration, gravity, and all of these other quantities should be familiar to you. Final and initial velocity, and the time of flight, and the displacement in the vertical direction, etc., etc. All right? Now, there's another dimension to consider, and that's the horizontal one. But gravity is vertical, right? It points down. It points at our feet. It points towards the center of the Earth, not horizontally. There's no component of the acceleration due to gravity that is in the x direction, either direction, okay? So when you look at the 1D equations of motion, for example, this one right here, okay, for the x direction, okay, which you can write down because this is a constant acceleration. The difference between this, where there's gravity going in right here, and this is that there's no acceleration in the x direction. This goes away, you multiply t by 0, this whole thing goes away, scribble, 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 and you're just left with this, all right? And the only equation of motion, albeit translated into subscript x instead of subscript y to indicate horizontal versus vertical, the only equation of motion that comes out to anything other than, well, that means that the final velocity has to equal the initial velocity, because there's no acceleration, right? Velocity can't change. Is this second one, where you start out with an equation of motion that looks, with my terrible handwriting, something like this, okay? That's an x, not a y, okay? If this is 0 right here, then this whole term drops out, and you're just left with this piece, which is what we see here in much nicer type, okay? So the equations of motion for a projectile in the horizontal direction are very simple. And the equation of motion for a projectile in the vertical direction are less simple, but no more complicated than what we dealt with in 1D. And these two things are independent. So the final velocity in the y direction really isn't affected by the initial velocity in the x direction or anything like that. The one link, and let me see if I can grab a different color. Come on now, please. Can I have the color? Well, no. All right, fine. In that case, we'll stay in blue and we'll say, look, time doesn't care what direction you're moving in, and so this t, you'll note, does not have a x component and y component. I think that's pretty clear from our reality and also in terms of the mathematics. Why there wouldn't be a horizontal and vertical component to time. It's not anything to do with the spatial movement of an object. It just is how many seconds have passed. So the time is ticking by as this object is launched and goes along its parabola and comes back to the Earth. And so if you're solving a problem in projectile motion, time is often the single link between what you can say about what's going on in the horizontal direction versus what's going on in the vertical. And a lot of the sort of problem-solving algorithm that goes on when you're talking about projectiles is to solve for time in terms of, say, vertical variables, get that time, and then substitute it into the horizontal equations of motion to find the thing that you want, perhaps the range of the projectile or something like that. Okay? So projectile motion is a pretty simple definition. We'll solve some problems with it in the next video. So there's a little preview, and I'll see you next time.